Hello everyone, my name is Kirill Horoshenkov and I'm Professor of Acoustics at the University of Sheffield. I also lead on the grant called Pipebots and I encourage you to visit this website to learn more about the grant. Today I'd like to talk to you about swarms of robots to inspect underground pipes. This is technology which we developed as a team. I'll give you a bit of background. So why do we need to inspect underground pipes? Because there are lots of these pipes in the UK. There are over 340,000 kilometers of clean water pipes buried in the ground and over 900,000 kilometers of sewer pipes buried in the ground. And you can see in this photograph, this pipe system is very complicated and nobody knows what real conditions these pipes are in. As a result, each time these pipes break, it happens all of a sudden. And as a result, we need to dig to these pipes to get to them, to replace them. So as a result, there is 1.5 million road works in the year in the UK to replace these pipes or to rehabilitate them. And there is a massive associated loss to the economy because of that. And also a majority of infrastructure maintenance is reactive, so we respond to something rather than actually anticipate it and do something before it actually happens. And one reason why it all happens is because there are not many technologies which can do it autonomously. If you look at what is happening now at present in terms of the inspection technology, maybe 90% or more of the inspection happening using CCTV. Basically, they build better crawlers, kind of robots which controlled by humans through the cable, and put these crawlers in the pipe, and this pipe basically inspected using visual means. There is a light and there is a camera, and the camera tells the operator a picture, and from the picture, operator decide what condition the pipe is in. This crawler is mainly used in sewer pipes because they're partially dry, so they're rarely used in clean water pipes. There is an alternative technology which actually we developed as a team, which has to do with the acoustic device, which we use to inspect sewer pipes. We insert a loudspeaker and array of microphones into the pipe through a manhole and send the signal through the pipe. Each time the signal reaches a obstacle or a something like a bad connection or broken pipe, reflections come back. We record this reflection and make analysis of it and decide where the problem actually is so we can do something about it. But again, this technology is delivered by a human, as you can see in here, through a manhole. It's not autonomous. Also, in terms of clean water pipes, there are two other technologies. One is using vibration sensors, as shown in this picture, where we attach mainly accelerometers to the hydrant above the surface of the ground, which connect to the clean water pipe, which may have a leak. And we do it at 2 points, and then we compare the signal at this point, again the signal at this point, and make a judgment where a leak occurs. Again, this technology delivered by a human is not very sensitive because it's delivered from outside, so it's prone to all kind of noises from traffic, construction activities, and so on. Another technology, which is called Sahara, it's to do with the insertion of a sensor inside the pipe on a cable. Again, it's done by a human being, and then this cable and the sensor, they're dragged by the flow along the pipe together with the flow, and each time it passes a leak, it records the signal, and the signal analyzed by operator. So, in the summary, all the technologies which we have now to inspect pipes underground, millions of kilometers of pipes in the UK, they all require human intervention. They also all cause a disruption at the surface because humans have to get in, they sometimes have to open manholes or hydrants, they have to dig out the road and so on. And they're all very difficult to operate in complex networks. So what is the solution? What we propose is to develop micro robots which are designed to work in underground pipe network and dangerous sites autonomously and cooperatively. Like in this simulation, we show that a real network of pipes, about 30 kilometers long, can be repetitively inspected by no more than 12 robots within a month, with no little human intervention. You can see these little nodes, they move around quite fast because we artificially sped them up. But they go around the pipe themselves and taking measurements and then bringing data back to the surface. How do we do it? We are lucky to get a grant from Engineering and Physical Science Research Council, which is called Program Grant. We started in March 2019, so we're just over 2 years into this, and we planning to finish in February 2024. This grant unites 4 academic institutions: University of Sheffield, where I come from, University of Birmingham, University of Leeds, and University of Bristol. It brings together over 40 researchers and over 40 industry partners. And again, if you want to know more about this grant, please do visit our website. So what we're going to do, we have a research program to build science and technology to enable this vision to happen. So first, we're going to build sensors which we deploy on the robots, which we develop. Then we also develop autonomous control for these robots, so they can actually work in an unpredictable environment below the ground in pipes. Then also, because all the system is supposed to work underground, where GPS signal can't penetrate and where there is no radio waves and other points of beacon points. So we have to develop a new technology for navigation to make sure we know where they are. Also, because they need to be controlled from above ground, and also they need to talk to each other, and also they need to send the data back. We need to develop communication and power solution for them to last. So this communication is not simple. Again, radio waves don't go through the soil very well. Therefore, we may have to build a technology based on acoustic wave on a visual light when we can actually communicate within the line of sight. Also, we try to make use of the emerging science and contribute to the other areas of research by providing solutions which we develop as a part of this grant. Also, we have a very strong user engagement plan, so to make sure that we work closely with water companies and their suppliers and present them knowledge from this technology, which are in auctionable form, so not too much information, not too little, exactly right, so the managers in water companies can make right decisions before the system requires severe intervention. Where we are now, so we are testing robotic solutions, developing for this purpose testing facilities in our laboratories and the universities. We're also making robots. This is our one of the first prototypes which we are testing in a wastewater pipe. We're also programming robots, so we make sure they can work with a very little processing power, probably either with a phone style processing power or Raspberry Pi. Also, we developing the way to navigate in pipes which are sparse feature environments, so using visual, audio, and other type of information. And also we're developing simulations to understand how sensors in these pipes deployed on robots will work collaboratively. There are a lot of benefits from this work. So we anticipate the main beneficiaries will be utility companies and their subcontractors who will be able to autonomously monitor their infrastructure on unprecedented scale. And they proactively rehabilitate buried pipes at a very much reduced cost. It's quite expensive now. We also feel that instrument manufacturers will be able to produce new sensing and rehabilitation solutions, so based on our science and technology which we'll develop. We also feel actually once this system is in place, the general public will benefit greatly from reduced failures and interruption to the services, so less dig, clear roads and so on, more sustainable supply, clearer water, and no blockages or flooding caused by incidents, and fewer road closures and less traffic disruption. This program grant is open for collaborations with external academics and non-academics partners. We also would like to engage more heavily in outreach and public engagement to make sure that public understands the benefits of this technology. Do not hesitate to get in touch with us. My email address is here, and this is the mail address of my colleague Ash Cooling, who is the grant manager. I hope you enjoyed this presentation. Do go to our website, and there are some presentations from the individual themes which I mentioned in my talk. Thank you so much. Stay well. Bye bye.